So, welcome everybody. I would like to give a non-trivial and pedestrian introduction to F-theory, as sort of a preparation for the F-theory focus week, which will be in 2 weeks. So this is just as a warning to the many experts which I'm seeing in the audience, and which probably shouldn't be here, that this is really going to be as basic as possible. So apologies if you're offended by the simplicity and by the many facts which I'm going to sweep under the carpet. So this is not going to be for a very technical discussion, but really so that we just get an idea of what we're doing, in particular aimed at people who are not working in the field. So after the unavoidable propaganda, I will review some very basic facts about type 2b Oriental folds, and in particular point out the problem of the 7-brane back reaction in type 2b Oriental folds, which then leads us to the concept of elliptic fibrations, as I said, in principle from the type 2b perspective, but which can be motivated also by duality with M theory. Then I will try to discuss a little bit about the mathematics, again very low-key, of these elliptic fibrations of the underlying Weierstrass model, and show one very cute application in terms of the D7-brane tadpole in F-theory. If there's still time today, or then beginning tomorrow, I will start discussing the gauge groups appearing on F-theory 7-branes, both from a sort of hand-waving M-theory duality argument, and then by going back from F-theory to type 2b, to strongly coupled type 2b, and try to identify the fundamental objects which we have in F-theory as the PQ branes, which are known also in the non-geometric description of just strongly coupled type 2b, even though we don't have a very good grasp on them in this context. Then I will make more contact with type 2b via sense limit, become a little bit more technical by upgrading the Weierstrass model to the Tate model, simply because this is the language in which most of today's papers on these F-theory gut models, for instance, are written. And if there are still enough people there by the time I get there, we can discuss a little bit about the spectral cover, but this will just be covered very briefly. So the question we would like to address is, what is F-theory? And the problem is that this is a very hard question to answer, because unlike other string theories, there is no, or there appears to be no fundamental underlying F-theory. There appears to date to be no fundamental 12-dimensional theory, the reduction of which is then what would be F-theory in 4 dimensions. So apparently, F is not full fundamental. However, there are other ways how to approach F-theory, namely by dualities, starting from various corners in the M-theory star. So there are different manners how to shed different light on F-theory. So it's accessible basically from 3 different sides. Primarily from type 2b. And here the folklore is that F-theory is type 2b with back reaction. From M-theory, here the folklore is that F-theory is M-theory on a torus whose volume goes to 0. So this is the famous Witten version of Newton's law, F equals m times a. And of course, we can approach F-theory from the heterotic side via heterotic duality, and there the folklore is that F-theory on K3 is the heterotic string on T2. So the bad news, we don't know what F-theory fundamentally is, but the good news is it combines features of 3 theories which we know a little bit more about, so that in fact we should imagine it as living at the intersection of these 3 theories. So we have type 2b, we have M theory, we have heterotic E8 theory, and somewhere in between is a regime which is called F-theory and which has parts in common from all of the three. What makes this useful in particular now for model building, because this is why we are here, at least why this workshop is here, is because it combines also phenomenological features of the compactification, say from the heterotic string and the type 2b string. Most importantly, so it combines properties of all three approaches. Most prominently, it combines the appearance of exceptional gauge groups, exceptional gauge symmetry, which is known in the heterotic string and in M-theory, with the localization of the degrees of freedom, which is also known in M-theory, but in particular in type 2b. So most prominently, we have the possibility to get exceptional gauge symmetry as in particular in the heterotic string, which is why the heterotic string is so successful in model building, plus localization of the gauge sector on branes, which of course is in particular a feature of type 2 or type 2b theories. And this is the reason why there has been the amount of activity that we have witnessed in the past 2 years or so on F-theory model building, simply because both these two features are very advantageous for model building, and the nice thing is that there seems to be a regime where both of them appear at the same time. So technically, if we want to...
So Timo, before you go on to sort of wordy level, you haven't mentioned moduli stabilization, so...
Exactly. I haven't mentioned many things.
No, I was just wondering if there was a reason for that. I mean,
yes. So, okay. In principle, it is clear how to stabilize moduli in F-theory. In detail, in practice, it is not. So the moduli stabilization sector is, one could probably say in this folkloristic manner, is the same as in type 2b. So we have instantons to stabilize, in this case, M5 instantons to stabilize the Kähler moduli, and we can switch on fluxes to stabilize the complex structure moduli without distorting the geometry too much away from Kähler-Yau. So this is the big advantage, or the big plus of type 2b and of M-theory and of F-theory over, say, the heterotic string, that there exists four-form flux, which can be used to induce a classical potential for the complex structure moduli without forcing us to deviate from Kähler-Yau. So we still have conformal Kähler-Yau 4 in M-theory or conformal Kähler-Yau 3 in type 2b. In the heterotic string, if we switch on H-flux, we get non-Kähler. So we have to use different methods to stabilize the complex structure moduli, say non-perturbative methods or whatever. But so this is another big plus. Thank you. But it's to do this in principle is of course hard. Understanding the M5 brane instantons is hard, and understanding the flux and really in F-theory is very hard. So the technical ingredients are first geometric. F-theory is a geometric description of type 2b. So we need to know something about elliptically fibered Kähler-Yau 4 folds. This is where algebraic geometry comes in. And second, we need flux, we need gauge flux, and flux to stabilize the moduli, G4 form flux. And to summarize the state of the art at the moment, I think elliptically fibered Kähler-Yau 4 folds are at least in principle understood. I mean, or there exist techniques to study and to understand certain Kähler-Yau 4 folds. I'm not saying that one has an overview or anything, but some of them can be understood quite in detail also, and then for concrete applications. Whereas the 4-form flux is still much of a haze, and one has to use other methods like the spectral cover construction, at least at the moment, to get around this. But progress is in sight.
Assume you had a duality between some F-theory model and some heterotic model, right? And assume on the F-theory side you knew how to stabilize the moduli with these fluxes, do you have any idea how that would carry over to the heterotic side? What it would look like? Not further physics? Or?
I mean, if it was anything like dualizing from a type 2B model, it would just turn into one of these non-Calabi-Gauss spaces, exactly as Timo said. So either non-geometric, which is a real nightmare, or non-cake.
There's also
So,
the issue that the lines fluxes in that theory don't dualize to anything in heterotic. You can't take them across. So a lot of the tools you want to use in the FA model just don't develop.
So if we were omniscient, it would probably not be a problem. It's just as far as technical, our technical skills at the moment are concerned. That it's, for example, that there's no example known of a vector bundle on a non-Kähler manifold on the heterotic string that gives rise to chiral spectrum. There are very few examples by Yao and collaborators, but for example, at the moment they are so simple that they don't even have a chiral spectrum.
So
I understand.
The question was sort of you have a model on the heterotic side which looks nice. You find a dual before you break supersymmetry, before you stabilize moduli. You find a dual on the F-theory side. Then on the F-theory side, you argue you can stabilize these moduli. Presumably, the spectrum doesn't change on either side. And then the question is, there must be some dual to that on the heterotic side, no?
There must, yes. I don't know the answer.
I think often Folds would be expected to be something like heterotic with an S flux, and the problem is that you don't know how to compute it. So it's just a technical question. I think we all believe in dualities in some sense, but we don't technically we don't know how to deal with it on the heterotic side.
Okay. So the original way to approach F-theory was from the type 2B perspective. So therefore, let us take a quick review, quick look at type 2B, what it achieves and what its problems are, and why we are led to F-theory, or might be led to F-theory. So type 2B Oriental Folds are, of course, as you know, a compactification of type 2B on a, say, 3 complex dimensional Calabi-Yau manifold, where we mod out by an Oriental Fold Z2 involution. So we compactify a 10-dimensional type 2B theory on a Calabi-Yau 3-fold X, and we mod out by the Oriental Fold action omega world sheet parity left-handed fermion number acting on the world sheet, and then importantly a holomorphic involution sigma, which is a Z2 involution holomorphic from X to X. Acting holomorphically. The resulting theory in 4 dimensions, of course, is n equal 1 supergravity. But due to the appearance of the Oriental Fold involution, we get a fixed point set, the so-called Oriental Fold planes. So we have O3 and or O7 planes. Depending on the details of our involution, we could also get D5, D9, but let's look at the O3, O7 case. And in agreement with this, or supersymmetric with respect to these, are D3 and D7 branes. And if one wants to look at phenomenologically interesting vacua, then both these are taken to wrap, to fill the 4-dimensional space-time and then wrap corresponding cycles internally. So the idea is that we have some Calabi-Yau 4-fold compactified down to R13. We have some Oriental Fold involution sigma mapping this 4-fold. Did I say 4-fold? 3-fold. Mapping this 3-fold to itself. The Oriental Fold plane is the fixed point set. So this is the, in this case, for example, the O7 plane. And then our D7 branes wrap various cycles on both sides. And in particular, to be symmetric under this involution, we need to take into account not only a cycle, but also the cycle image. So if we have these 7 branes, they wrap holomorphic for supersymmetry, holomorphic 4 cycles, gamma A, plus we need the same amount of D branes along the Oriental fold image. So a cycle, a brane on a cycle and on its image. If the D branes are away from the Oriental fold, the way how I drew it here, or more generally, if they are not invariant under sigma by themselves, then a stack of n D branes carries gauge group un. So if gamma A not equal to sigma of gamma A, so if the cycle is not invariant, then n D branes leads to gauge group un. And if the cycle is invariant, the spectrum is subject to the Oriental fold action, so we get SO or SP gauge groups. So if the cycle is pointwise invariant, then in general we get SO gauge groups. Roughly speaking, we get SO gauge groups. And if it's just invariant as a whole, but not pointwise, invariant only as a class, then roughly speaking, we get SP gauge groups. But to determine the exact gauge groups depends on the details of the Oriental fold projection, and is in general a tricky business.
So so the pointwise invariant means that literally each point on the brane gets back.
Exactly. So if the brane wraps the cycle on top of the O-plane.
Yeah. Whereas the other one
would be something like this, where the cycle is mapped to itself, but not pointwise.
So in other words, the cycle stays in the same homology.
That's correct. Exactly. But as I said, even then, it's not totally clear a priori if it's really an SP gauge group. It depends on the. So in general, one would need to decide that by a CFT description, but of course this we usually don't have, so one would need other methods. And there are very intricate complications discussed by, for example, Mu and collaborators and many others dealing with these. Dealing with this issue. But the point is we get unitary gauge groups or SO SP gauge groups, nothing else. So there are 2 things which I would like to stress about this Oriental fold approach, and which is different from the F-theory approach. So so 2 important points. First, Oriental folds are by definition treated, in the Oriental folds, the D branes and the O planes are by definition treated in the probe approximation. This means that we do not take into account any back reaction of the O planes and of the D branes on the internal geometry. We simply put in the branes and completely neglect its back reaction. So we use a probe approximation. We completely neglect the back reaction of the branes, of the O planes, and of the D branes on both the geometry, so the metric, and the Ramon-Ramon or the other Neuve-Schwarz background fields. What we do, however, is
have a back reaction factor.
Because the O-plane,
Do they carry energy?
they carry energy, they carry negative energy, yes.
How do you see that?
No. They, for example, the Chern-Simons action of the O-plane couples, or via the Chern-Simons action, the O-plane couples to the Ramon-Ramon fields, and it does so with exactly the opposite sign than the D branes. So it carries negative charge, and also negative energy. So how one would actually see that is, again, in a CFT approach, by extracting the charges in the Neveu-Schwarz and the Ramon sector from, say, one loop computation. Basically, this was the computation done by Polchinski, seeing that the O-planes talk to the background fields with exactly the opposite charge, both in the NS and in the Ramon sector. So we don't explicitly compute the back reaction, but we make sure that the integrability conditions for the field equations of motion in presence of planes and of the O-planes and the D-branes are satisfied. So we make sure that there are no topological obstructions to finding a solution. So the integrability conditions these are solved. This is an important part of this whole business of finding compactifications, or of defining compactifications. And these, from the supergravity point of view, what one does is one solves for the Bianchi identities for the Ramon-Ramon or Neveu-Schwarz fields. So the Bianchi identities for the Ramon-Ramon and Neveu-Schwarz fields are satisfied, and technically these are the famous tadpole cancellation conditions. So tadpole cancellation conditions. For example, the 7-brane tadpole cancellation condition says that the charge of the Ramon-Ramon charge of the D-branes equals, in their sum, the Ramon-Ramon charge of the Oriental Folds planes. So for the D7, we have the charge, the homological charge of the D-branes and their image have to add up to the homological charge of the 7-brane. In this case, so this means that overall in this compact space, there is no total charge, no total flux lines, so that we can now find a solution in principle, even though we don't care to do so. And similarly, for the D5 and D3 brane tadpole cancellation conditions deal with the induced charges, but let's not go too much into details at this stage. So what I wanted to say, we have a probe approximation, we have topological consistency conditions solved. This is important, but we don't look at the back reaction as such.
Question: is it for the fluxes, flux contribution to the tadpoles?
Yes, these would come in the D5 and D3. So if, for example, if we have gauge flux on a D7 brane in this case, it induces a D5 brane charge. So these have to add up to 0 among the D7 branes. There are no D5 brane charges from the O-planes. And this is the linear term in the term-Simons action, and the quadratic term gives rise to a D3 brane charge, together with the curvature correction from the D7 brane and the curvature conditions from the O3.
What about bulk fluxes? Do you also take them into account in these tadpole?
They must. The Ramon fluxes must feed into the D3 brane tadpole cancellation condition, if we have some.
Do you also take them into account locally, or just in the integrated?
Only in the integrated form. Only in the integrated form. So, yes. The charges are not cancelled locally. Charges are only cancelled globally. And this is why there is something to worry about as far as the back reaction is concerned, because locally we have charge, it's just that overall the total amount of charges vanishes as it must on a compact space. The second feature of these, or it's actually related, is that we are in a perturbative regime. Perturbative meaning, since we don't care about the back-reacted solution, we in particular don't care about the solution for GS or for the dilaton. So we simply put it to very much smaller than 1 by hand. So we put GS very much smaller 1 by hand or by definition, without caring whether or not this is well defined globally. And we don't care about a non-trivial profile of the dilaton. So this, in principle, this is of course highly problematic. In principle, all of this is is correct only if, as you pointed out, only if we cancel the all charges locally by, say, having no smeared flux away from the brain and putting all from the O plane and putting all the D branes on top of the O planes. So, strictly speaking, this is okay, or this is really correct, only if all charges are cancelled locally. So only if we place all branes on top of the O planes, say.
But it must be a sort of good approximation when you're near that as well, right? If I just take the case where they're on top of each other and I separate them off slightly, it must still be a reasonable approximation.
Yes. It is not unreasonable. That's the second point I wanted to make, but it's just not exact or exactly correct. But the reason why it is justified is because for general brains, the back reaction is such that it vanishes asymptotically. So we have asymptotically flat space away from the brains. So.
How important is the way that the D7s are embedded in the geometry? I mean, you have to choose embedding, right? How the D7s
Yes.
are after the 4th cycle.
Yes.
So do you have cases where you understand that well?
The embedding is such, well, that is the point of F-theory, basically, to try and understand this dynamically, the dynamical interplay. Maybe it'll become more.
Okay. When you say you put D string to 1 by hand, how are you stabilizing the dilaton?
It is not stabilized at this stage without then free-form fluxes, say.
Right, but you have those, right? So you can turn those off.
Yes, but then one has to make sure that they are stabilized, that the overall, that the asymptotic value, which one takes to be the exact value by hand, is sufficiently small. So one could screw this up even at this level by stabilizing the dilaton in the wrong regime.
There must be some statement as to what the scale is as you move these brains apart from one another, so you can no longer take the dilaton to exactly a constant. What sets the scale as to how far away you're allowed? You can take them when you can no longer make that approximation.
I think in F-theory there is a more precise statement of how you can actually do it. The F-theory solution will adjust itself dynamically so that, say, the negative charge of the or mass of the O plane is not an issue anymore.
But I think as a flat direction, or is there a potential on climbing to move the brains apart?
I think in F-theory it will not be a flat direction anymore. It will adjust itself dynamically in such a way that the distance is exactly such that there is no problem more with, say, the negative charge of the O plane. This is the splitting of the O planes, of a naked, say, O plane in F-theory.
Here it must be a flat direction, right?
Yes, here is flat. Here we don't take into account the dynamics at all.
Greg Susie, there are flat directions like this. We've seen the standard 2B.
Yes, and yes, there we don't take all of this into account. There we don't worry there we also don't worry about the fact that the O plane has negative charge and that the supergravity breaks down near it.
So, did I understand correctly? You said if it has negative, the O plane has negative charge, it means it has negative energy?
Correct, yes.
Charge is not usually...
No, so the brains, thank you. The O planes are BPS. In that case, their mass or their tension is equal to that charge under the Raman-Raman field. Absolutely. So why this is just now as an apology of what one usually does. Why is this okay, at least in principle? The reason is that asymptotically, the back reaction of a brain goes to 0. Not in type 2b, but for general brains. For general brains, not for, at least not for p equal to 7. So what's the usual argument that one runs in order to salvage this, at least approximately, at least asymptotically? One says that, so suppose we have a dp brane in 10 dimensions. So this is an object that is point-like in the ambient 9 minus p dimensions. It's a point-like charge in the normal 9 minus p dimensions. So roughly speaking, what one has to solve in supergravity is now a Poisson equation for a point-like source in 9 minus p dimensions, roughly speaking. So roughly what we get is for whatever kind of field, delta Laplace phi equals delta of r, where r is the radial direction in these 9 minus p dimensions. And this has the solution that phi of r dies off like phi over 1 over r n minus 2. And if p not equal to 7, this goes away, this fades away, meaning that far away everything is fine. So as long as we go to large volume, if we like, sufficiently large volume, the back reaction effect should be negligible, or is negligible, for p not equal to 7.
What is sufficiently large?
Yeah, this is the same question again, how to really quantify it.
But I guess that this tells you what that is, right? It's the mass of the source relative to the gravitation. So it's basically determined by the mass of the brane relative to gravitation.
Right. So in these solutions, for example, if one has a BPS brane solution, one has a warping factor, this harmonic function h, and this goes like 1 plus some, I think, number times gs times the number of the branes times r over n minus 2. So this guy vanishes for r to infinity, and to see how far it how fast it vanishes, this is a question of the coupling and of the number of branes, so to speak, so of the mass. Yeah, but it's tricky to make this dynamically. I think it's tricky to make this more quantitative. Anyways, it was just meant as a motivation to now look a little bit closer, because this is what F-theory was designed to do. Namely, in principle, we have problems with this. Many of these were pointed out by you already. So first, the O-plane has negative charge. So the solution near a naked O-plane is not well defined. One would have to consider smeared solution in supergravity. A second thing, as you also pointed out, is that, of course, the dilaton varies in general.
Negative tension.
Oh, sorry, yes. Negative mass, I wanted to say. Tension, yes, thank you. I think the supergravity is not really well defined. We should actually ask the supergravity experts on that.
But it depends on you believe in positive energy conditions or not. And you have to show that these things cannot be moved around. You cannot resolve this into something that's near. You have to keep the singularity.
But these are non-dynamic.
Yeah, there's a constraint that you can't get instabilities from the negative.
Right, but if you try to mirror them, just put them as a source of supergravity, so you get something that is very behaved, then you have problems. So you have to keep them singular.
Well, in practice, we only solve the supergravity equations if we're far enough away from the source to the spring length.
I mean, is the claim just that the curvature is becoming so large near to this object that the upper correction is
That is certainly, I think, true.
well, then,
You know, really, they're stringy objects. And, for example, you have the constraints that they can't move and give you instabilities as well. So you can treat them as effective sources, but you ultimately have to treat them as stringy objects.
So in CFT, it would, of course, be okay. The CFT is well defined.
Yeah, that's the problem.
Yes. Yeah, but in general, we don't have. But in addition, we don't care too much because asymptotically it's fine. I think this is the logic. We close our eyes, so to speak.
Is it not something as simple as if you look locally to it, if you have the wrong sign for the tension, then you get a minus sign in the harmonic function, and so metric is just singular, not on the brane, but near it?
Yeah. So you get a divergence, final distance from the brane. So divergence in what? A curvature. Curvature.
Yeah, it's a border alpha prime, and there's some power of the coupling, I guess. Or something. But yeah, so you have to stay away.
I thought the bar factor went to 0 as you went to the brane, and then the dilaton using these alpha solutions, but the dilaton kind of goes deeper and deeper into the weakly coupled regime as you approach the D brane.
But this is for a D brane. This is for a D brane.
Is the solution different there? So there's a defect angle.
Okay. I mean, here also the dimensionality, of course, comes in. I wasn't.
I was thinking specifically about D7 brane.
Okay, so for D7 branes,
The 07 plane's the issue, is the negative tension.
If I have an 07 plane, is there something? If I have a small negative tension, is that in principle that?
So the 07 plane in F theory will not even exist as an object. So either we put all the branes right on top of it, so that the charge is cancelled and the negative tension is cancelled, then we have no issue. Then we are in the case where we can have exactly constant dilaton. Or as soon as we move one brane away, the system will adjust itself dynamically. The O plane will split into two branes which do not have this problem anymore.
It is the claim that if I approach the 07 plane that's not screened by a bunch of D7 branes, that either the dilaton or some curvature during the divergent at that point?
It would be if in type 2, but in F theory this is resolved such that the brane splits and the two objects then are well behaved.
So they would have a supergravity solution?
Yes, in the F, yes, they will.
You're trending for curvature, so curvature can have negative mass implications.
But the claim is I can't have small curvatures everywhere in that neighborhood somehow. Even though it starts off being flat.
So after the two branes have split, they are at such a distance that if one gets closer than the separation of the two branes, non-perturbative corrections will kind of salvage you, and so that the supergravity is not the theory to solve anymore.
Non-perturbative in string coupling?
Yes, yes. In string coupling. Yes, yes. In string coupling. Okay, we were now discussing what happens close to the brain, but even that I didn't take into account. I was discussing what happens away from the brain, so far away, so the asymptotic region. And even though in all these models we have problems close to the solution, say the O plane, for D7 branes the situation is even worse because we have problems also away from the 7 brane. So this is now the additional complication. So for p equals 7, so in addition to these to the near brane, or rather near plane behavior, we also have long distance effects. And this is where p equals 7 comes in, and this is why in this case it's particularly important to have somewhat of a better grasp, at least conceptually. So this is where then the F theory is meant to kick in. So what happens particularly for 7 branes? Sorry. So the action for the 7 brane is, of course, the dBi action plus the Chern-Simons action. And in the Chern-Simons action, the 7 brane couples to the Ramon-Ramon 8 form, and then if we have flux and via curvature also to the lower dimensional forms. So we see that we have an electric coupling to C8, and in other words, a magnetic coupling to C0, which is the magnetic dual of C8. So we have an electric source. The 7-brane is an electric source for C8. And it's, so in other words, equivalently, it's a magnetic source for C0. And C0, the Ramon-Ramon 0 form, is what appears, of course, in the complexified axiodilaton C0 plus I over GS. So already from this one sees that it also talks directly, because these are combined in one superfield, to the string coupling already via this topological term. This is, so to speak, what makes 7-branes special. In fact, it speaks only via the topological term to the C0, it turns out.
I have a naive question about that reaction. So if I take a 7-brane in 9 dimensions, it's analogous to a string in 3 dimensions.
Yeah.
And we know that there's, you get just a conical structure.
Yes, I'll come to this right now.
That's the issue, part of it.
Yes, I'll come to this exactly now. So what, as you anticipated, a D7-brane looks like a string from the ambient, in the ambient 2 dimensions in 10-dimensional space-time. So we have here our 2 directions, x and y, which we can combine into one complex coordinate. So what we have to solve for, and what was solved for by Waffer and collaborators even before F-theory was born, was for a string, so to speak, a cosmological string, or whatever you want to call it, in 2 ambient dimensions. So how can one find the dilaton profile in this context? So first of all, by n equal 1 supersymmetry, it is known that the dilaton has to be holomorphic. So once one has a profile for C0, holomorphic profile, one can continue it to the profile for tau. So the easiest way to find the profile for tau is to write down the equations of motion. Basically just do what we just did for in smaller dimensions, the equations of motion for the field strength F9 of C8, to which the D7-brane couples, in the presence of this source. So the equation of motion for F9 is d star F9 equals delta Z minus Z0 if our 7-brane sits at Z0. This comes just due to this source here, and here we have the usual delta function. The usual delta function in the ambient dimensions. So one doesn't even need to solve this equation. One can simply use Gauss's law and integrate this equation. So we integrate the right-hand side to 1. So the usual stuff. So this we can now transform into an integral, since we are basically on a complex plane, along our brane position, star F9. Star F9 is the magnetic dual, or the electric dual of F1. So we have dC0 on C1 is 1. So dC0 has to go like 1 over Z, and therefore, as Robert said, the C0 itself has to exhibit the usual solution for a conical singularity 1 over 2 pi I ln Z minus Z0 plus regular part. So this is the solution, so to speak, close to the brane. There can be now regular pieces which don't appear in this integral. And therefore also tau of Z is 1 over 2 pi I ln Z minus Z0. That's regular. So in particular, it already from this one could guess that now, in addition to the small range problems, there is a long range effect, because the solution for the dilaton does not fall off in any way for the complex dilaton. And if one looks more closely, and I'm not going to discuss this now more, at the actual metric of the ambient space, then indeed it turns out that there exists a defect angle far away from the brain. So no matter how far we go, we can never get rid of this defect angle. We can get rid of this defect angle if we are sufficiently close to the brain, so to speak. Locally around the brain, we don't see this defect angle in the metric, as it turns out. But we have other problems there. So we have yeah, the exodilaton, actually.
C0 is the argument.
C0 is the real part.
Yeah. I just think that IO prime makes it look like it's the imaginary part. It's kind of like a log. I don't know if that's important. It's just,
But by Holmhoff, so C0 and tau have to have the same behavior.
Yeah, but C0 has to be a real part.
It has to be real. Okay, yeah. So I was faking a little bit. I agree that I was faking the computation a little. But one can. So if one really looks at the metric from the Einstein equations, then this is what we will get. So this was.
I think you're just saying that C0 has to be the angle, so it integrates to 2 pi, and that's the real part of, the imaginary part of the log, and then the whole working function is the log.
Okay, so we put this into quotation mark, but. So it's a long-range effect. It's not totally obvious from here, because this is just the solution close to it. But if one looks at the exact solution, which would be much more time-consuming now, then one would see that there is a deficit angle. And there is another puzzling thing about the dilaton. Namely, we have obviously here a holomorphic branch cat, or a monodromy. So as we go once around the D7 brain, the exodilaton jumps by 1. So the logarithmic branch cut means that as we encircle the 7 brain, the exodilaton tau goes to tau plus 1. A monodromy. So indeed, the dilaton shifts by a real part, as you said, yeah, and that's the way how I should have phrased it from the beginning. So this is, of course, something very strange. So it seems like the supergravity solution is not even well defined in the presence of such a 7 brain. But what comes at our rescue, of course, is the SL2Z symmetry or duality group of type 2b in 10 dimensions. So this is consistent with the type 2b supergravity due to the classical SL2R, which then gets further broken, symmetry. So let's review this very quickly. So if one takes the supergravity in 10 dimensions, in, say, Einstein frame preferably, then one sees that there exists, that this action is symmetric under the transformation tau goes to A tau plus B over C tau plus D. And the two fields are related by AB CD, C2, B2, where this is a matrix M, and the determinant of M has to be 1. So non-zero, and then can be rescaled, and the 4 form goes to itself. So this is known to be a symmetry of the type 2b SL2Z, of the type 2b action, just by looking at the action Einstein frame. Classically, it's SL2R, and then non-perturbatively by the presence of d-1 branes or d-1 instantons, it's broken to SL2Z. So non-perturbably, SL2R is broken to SL2Z, simply because we have a d-1 instanton. So in particular, this is an object that couples in this manner to C0. So C0 is allowed to shift only by an integer for this still to be a symmetry. So this breaks it exactly down to SL2Z. So in other words, as we go once around the 7 brane, we have to transform all the background fields consistently, not just tau, or not just C0, but all the background fields consistently. And this is therefore not a conceptual or fundamental problem. So we see that this, in general, non-perturbative SL2Z symmetry plays an important role, comes into the game automatically in the presence of 7 branes.
Sorry to interrupt again. So that means that the monodromy is not really useful for cosmology. One couldn't use the monodromy.
Probably not, yes. Yes, this would be very nice, yeah. I think so too. Because it's, yeah, as you say, it's probably just a redefinition. That's my interpretation, but yeah, we could discuss this maybe if it really enlarges the field space, say, of your axion. But I would suggest, I would suspect it isn't. So this appearance of the SL2Z symmetry leads immediately to the concept of elliptic fibrations, namely the indigenous insight of buffer was now to identify the exodilaton with another object that has a natural transformation property under SL2Z, namely simply the complex structure of a torus. So at this stage, this comes completely out of the blue, but it's just motivated by the fact that the axion transforms like the complex structure of a torus. So we observe that we can identify tau with the complex structure of an auxiliary torus or elliptic curve T2, auxiliary meaning that here it has really no physical meaning other than being a bookkeeping device for our T2, for our exodilaton. And we furthermore identify the SL2Z action as the action on this torus. So once we've done this step, we are led to the conclusion that the system can be described by looking at the variation of the complex structure of a torus around the 7 brane. So if we go around the 7 brane, the exodilaton varies. Equivalently, we could say we have some auxiliary 2 torus which takes into account this variation and which has the property that as we go around once, there is a well-defined action of this SL2Z, so that physically nothing much has really happened. So, so the variation of tau in presence of a 7 brane means that the complex structure of T2 varies. So in other words, we can describe the situation by an elliptic fibration, a non-trivial elliptic fibration, where we have a T2 fibered over our space in which the D7 brane is embedded. So we have a fibration T2 fibered non-trivially, so varying complex structure over, at this stage, 10-dimensional space-time. And there is an important thing to notice. Only the complex structure of this torus has any physical and, so to speak, quote-unquote, meaning. So only the complex structure of the T2 has a physical meaning. The Kähler form has no meaning whatsoever. Simply, we have no place, nothing to identify with it with. Something that we will encounter also from the F-theory point of view. So what happens? So locally, near the D7 brane, the exodilaton tau, which is like 1 over 2 pi I ln z minus z0 plus stuff, goes to plus I infinity. So this means the complex structure of this torus diverges, or the torus itself somewhat degenerates. So the complex structure degenerates, and one can picture this, for example, as follows. So we have our famous torus as a lattice in C2. We have an A cycle and, say, a B cycle. And at the position of the 7 brane, say the A cycle shrinks to 0, the torus degenerates in such a way that the complex structure goes to infinity. So tau to I infinity, so to speak, that the A cycle goes to 0. So the picture, the intuitive picture, again, is very simple. We have here our D7 brane. Now, as we move around in our ambient z coordinates, we are literally thinking of having a T2 torus, a T2, an elliptic curve everywhere over the space, which shape, its shape varies, and as we go at the position of the 7 brane, one of the cycle goes to 0. So the torus, so to speak, pinches off. One of the cycles, say this cycle here, has shrunk to 0. We just have one single cycle, and this is a degenerate torus of the topology of, say, a P1. So here, the T2 has become a P1. So a cycle pinches off.
But doesn't it just become a circle instead of a torus?
It's just
one of the radii went to 0, right? So instead of having a two-dimensional surface, you get a one-dimensional.
But only at a point of the
It's only at a point that's equal to 0, but the whole torus pinches, no?
No, you have to keep the area fixed.
It's really
because the Kähler form has no meaning, so you have to normalize the area to 1. So
or to 0, yeah.
It's really like Heater. It's not that the whole thing becomes thin. That's what we would suggest.
Yeah.
The radius is not uniformly shrinking. It's only it's really the pinching like that.
So since
the A cycle is the whole radius. Isn't a cycle the whole radius of one cycle? And if that goes to 0, doesn't it go to?
It's a minimal radius for the class of that cycle.
The only relevant thing is the complex structure.
Yes.
Right.
Can I not think that this is infinitely within infinitely long torus?
I mean,
maybe in the simplest case it is a thin torus, but then it can be more complicated.
of course, this is just a single. This is just for a single 7 brane.
But so in the simplest case, it just becomes infinitely thin.
Well, since the only relevant thing is the complex structure, there are many different ways of describing it. You can describe it as a very thin torus with a finite height, or a very long torus with a finite width, or
The difference
the way
is,
he's described it there.
the difference is that if it pinches at a point, it looks like a P1.
Yes.
If it becomes an infinitely thin, it's never a P1. It's just a T2, just infinitely thin.
Okay, the case that becomes a P1 is really when you have SU2. I mean, it's a more complicated.
Yeah, this is one single 7 brain. 1 7.
Yeah.
I'll cover the more general
In that
case.
I would say that's not the case where you get P1 yet. Right? When it's just 1 7 brain.
Yeah.
I'd say you need an A1 singularity, right, to get a P1.
No, you need 2 P1s to get an A1 singularity because the 2 P1s give you the extended Dynkin diagram. If you have a P1, you get nothing, so I1 singularity. And for an SU2, you need 2 singularities, and this is the extended Dynkin diagram. So I think this is.
So does it become a P1?
Yes, it becomes a P1.
But then I don't understand the geometry here.
I mean, if you draw this picture like your buffer to that point, what Stuart says, you just take the above.
Take the A cycle to 0, it doesn't become a P1.
It's
Most thing too is S1 cross S1, right? If you take S1 to 0, you're left with an S1. So that's
But again, the relevant thing is complex structure, and so the P1 with the points identified has the same complex structure. You don't care about the metric, you don't care about the length, it's the relative length.
Yeah.
Describe factorization of string amplitudes. We don't draw infinitely long cube necessarily, we draw a conformally mapped diagram where the
I'm just talking about the topology of it. The topology doesn't seem to be the topology of P1, so I just don't see it.
The pinch point, you're gluing both of them together
Yeah.
with a cube that's conformally mapped to a point.
Right.
That the infinitely long cube is conformally mapped to a point. Just like
Mapped to infinity, yeah, and to 0.
The string scattering diagrams. The factorization limit is
Could you maybe draw a picture so I can understand what you're saying?
So you take the tubes together, right, and pinch them off.
Open that P1 and
like this, and then you pinch,
No.
but you map it to infinity, to a single point.
The one on the left, just open up a little bit, 2 factorization points, include them with a long thin tube in the center.
Yeah.
So the one cycle, it's just the homology class of that one cycle that goes to 0. What do you mean?
And so you can use
Right.
a local rescaling of the metric to draw it in different ways. You can draw it with the cycle going to 0 just in one place. Think of it as a real geometry, like he's done. Or you can draw it by using a local Weil rescaling, you can draw it in one of the other factions, like a long skinny tube or a very short tube that has finite width. It's all just different by Weil rescaling. Well, I just described the pictures that are already drawn.
If you have an infinitely long tube between that thing,
But
you still get T2.
But you map the point to infinity.
Right. If you take this, let me just fix David. So take this picture where that little bit of tube is getting really, really small, but the rest is fat. That's equivalent via a Weil rescaling to these other different pictures of this little.
So you keep one cycle and destroy, so to speak, destroy the other. It's topologically has become topologically trivial. The one cycle pinches off. Maybe we can discuss this.
Yeah, we can discuss it later.
Where was I anyways? Okay, well, yes. So one of the cycle pinches off. Maybe this is the way how one could phrase it without arising the confusion. Which cycle pinches off is, for a single brain, a matter of convention. SL2Z will act on the different cycles and map them to one another. Locally, we can always use an SL2Z symmetry to make sure that, say, it's this cycle here which pinches off. But as soon as we have two different 7 branes, there is an invariant meaning to which of the cycle is the one that pinches off. That just for later references.
Two branes on top of each other, or two
Both.
branes at different points?
The same. Both on top of each other and on different points. And putting 2 branes on top of each other. So if a PQ cycle shrinks to 0, it maps to a PQ brane in type 2b, or pinches off, or whatever you want to call it. They are related by SL to Z, and the appearance of 2 PQ branes of different type, both on top of each other and away from each other, is what gives rise to non-perturbative. That's just an outlook. I will discuss that in detail then in this 4th part. Oh. So we have seen the torus as a bookkeeping device from type 2b. But the appearance of the torus, so how much time do we have actually? 5 minutes. So let me be very quick here. The appearance of the torus can also be approached from the M-theory point of view. So be f from M, and I'll now be even more sketchy than before. So irrespective of all these considerations, one can use a certain duality between M-theory type 2a and type 2b to motivate the appearance or the relevance of a torus for the description of the exodilaton. So if we compactify 11-dimensional M-theory on some torus, T2, which will be related but not identical to the one appearing here, times in 9-dimensional space, we now use a peculiar limit where the volume of this torus goes to 0, which is the reason why also the volume of the torus will not appear on the type 2b side. So we write the torus T2 as the product of 2 1 cycles, the A cycle and the B cycle.
M-theory for you is from heterotic, or is it type 2a?
It's 11-dimensional supergravity with, at this stage, 11-dimensional supergravity, in principle with M2 and M5 branes. So 11D supergravity. Thank you. So we reduce it along a torus with the product of 2 circles. And we now take the limit of the volume of the torus to 0 in the following fashion. So the first one is first we identify this A cycle as the M-theory circle of type 2a, so to speak. So we take the radius of S1a to be small, so that we get type 2a on M9 times S1b with small coupling. So Ra goes to 0 means we have weakly coupled to A on M9 times S1b. And the second step now is to do a T-duality along S1b. So we do T-duality along S1b. This gives rise to still weakly coupled type 2b on S1b tilde with radius RB tilde like LS now from the to A point of view over RB. So as we take the limit RB going to 0, then RB tilde goes to infinity. So we decompactify and get 10-dimensional type 2b on M9 times R, so on M10. So as RB goes to 0, we recover 10-dimensional type 2b on M10. And the point is that, very roughly speaking, the type 2b dilaton appears as the ratio of the two radii in type 2a. Of the two radii in 11D supergravity. Just by following this chain of dualities, by doing this M-theory reduction and by doing the type 2b reduction with using the Buscher rules. So very roughly we get that the type 2b GS goes like, in the string frame, in the Einstein frame, sorry, goes like R10 over R9 in the M-theory. Very, very roughly speaking, which basically would be the imaginary part of tau, roughly speaking. So this is how, so in other words, so two important things to remember. First, we need the torus, the volume of the torus to go to 0 in M-theory. Not every M-theory compactification on two torus will give rise to a type 2b compactification. We really need the torus volume to be 0. This is why there's no appearance of a volume or Kähler form of the torus on the F-theory side. And then the part of this torus in the M-theory becomes part of M10, the 10-dimensional space, namely S1b, is T-dualized, so to speak, into the 10-dimensional space. And part of it just goes into GS. But what stays is the ratio of the two. And this will map by using by explicit computation to GS, and can now be identified as the imaginary part, say, of the complex structure of the original torus. And the same for C0, which is related to C1 and the circle vibration in this process here. So we get type 2b. If the torus was varying on the M-theory side, the complex structure will be varying on the type 2b side, and therefore the torus as such again in F-theory. So we don't recover F-theory immediately, but only again by making this this identification. And this is really a peculiar limit, and it's in general really not easy to explicitly trace back things from one side to the other. For example, when it comes to gauge flux, etc., it's really tricky. Okay, so the upshot is if we have 4-dimensional compactification of type 2b on M10 equals R13 times our Calabi-Yau manifold, our quotiented out. The physics of this, at least the D7 brane and the exodilaton related physics of this, is described by the geometry of an elliptic vibration y T2 over B, where, let's call it this way, B6 is basically x over sigma. And again, the physics of the 7 branes and the physics of the exodilaton is now encoded in the physics of this torus. So in particular, this is something for which I think we definitely need the M-theory picture. I'm not aware of any other way how to see this. For n equal 1 supersymmetry on the M-theory side, the corresponding Calabi-Yau fourfold has to be, the corresponding fourfold has to be Calabi-Yau. So then one conjectures that also on the F-theory side, the fourfold has to be Calabi-Yau. So for n equal 1, and this is where the M-theory picture really necessarily comes in, n equal 1 supersymmetry on Y from M-theory requires that Y is Calabi-Yau fourfold. And this is then taken over to the type 2b or to the F-theory side. So not every elliptic vibration will do, but we need a Calabi-Yau space for n equal 1 supersymmetry.
When you showed this picture with this D7 brane as a string, and now you take the Oriental Folds as a manifold, can you draw a picture like that for the Oriental plane as well?
In principle, yes. So it will all wrap a cycle now. I'll come to this right now. It will, of course, so far we have been only in 10 dimensions. If we now really compactify, then in the 2B picture, our D7 branes wrap a cycle gamma A a 4 cycle. Similarly, the O plane, the O7 brane, also wraps another cycle. From the F-theory point of view, this means that the torus degenerates over a particular 4 cycle in our base B6. So T2 degenerates along a particular 4 cycle in the F-theory picture. And the same also for the Oriental fold.
When you say equals 1 supersymmetry on the M-theory side, that's...
Sorry. Sorry, okay.
Yeah, that's in 3 dimensions a priori, so it's the equivalent of 4 real supercharges and not the minimal amount of supersymmetry you could have in 3 dimensions.
Yes, but yes, exactly. Precisely. So it's the one that corresponds in 4 dimension to any one. So 4, yes, thank you, 4 supercharges. In the 3-dimensional compactification.
Sorry, I'm missing something basically. So you're presuming you know that the M-theory compactification preserves a certain amount of supersymmetry in 3D theory.
Yes.
Why does that tell me that the M-theory compactification should preserve a certain amount in
This is the conjecture. From my point of view, this is the conjecture of the duality. I'm not aware of an independent way just from the type 2B picture. I mean, given this Calabi-Yau property, we will probably never ever show now for time reasons that say the D7 Chapel condition arises. So there are consistency checks. Maybe one could approach it from this way too, but the usual way how it is understood is this is one part of the conjecture, if you like, which of course has checks. One of them is the 7-brane tadpole. And the actual conjectural part now is is that we go away from our original to B picture and really take this Calabi-Yau fourfold literally. So we say, so far we've just recovered that whenever we have a brane, then the torus degenerates. But now we completely go away from type 2B. We simply take an elliptic Calabi-Yau fourfold, and then we conjecture that wherever this fourfold degenerates, we have a D7 brane. And this may be a picture that is not necessarily in one-to-one with the type 2B anymore. So we really let the geometry decide for us now where the brane sits. This is now the conjectural part, or one of the conjectural parts. So the conjectural part includes, in particular, that every consistent way to say paste together singular fibers into a consistent Calabi-Yau fourfold, elliptically fibered Calabi-Yau fourfold, that every such way gives us the dynamics of a consistent 7-brane configuration. And this is, of course, a big step to do. But once one buys this, then the problem really reduces to doing geometry. One can learn many things about the 7 branes, which one would not learn just from a 2B perspective. And the fact that, as always in these dualities, I guess the fact that one has non-trivial checks on some of them, some of the resulting features, is then taken as evidence or whatever. So in particular, we will see that the 7-brane tadpole is automatically incorporated, at least in cases where one can compare, and the exodilaton is believed to be taken into account properly. So we have seen that we need to learn about tori, we need to learn about their degeneration and how to paste them together. So we need to understand an efficient description of a torus and its degenerations, and second, about the fibration, how to promote such a torus to a manifold in order then to read off physical data from this. So there are different ways to think about tori. One efficient way to think about a torus is as a hypersurface in a weighted projective space, or more generally as a complete intersection in some projective space. So basically we now, so of course all this had been done already by the mathematicians, so we now need to, need to try and use what they had found for us. So one way to represent a T2 is as a hypersurface or as a complete intersection in some weighted projective space. So the most common, but not the only one, but the most commonly used, and probably to some extent the most general in this class, is to view the torus as a hypersurface of degree 6 in a weighted projective space of weights 2, 3, and 1. So what does this mean? We take three complex coordinates x, y, z, complex. We identify them in order for them to form homogeneous coordinates of p, 2, 3, 1. So we quotient out a scaling relation, one complex scaling relation. This gives us a 2 complex dimensional space because this is complex. So this gives homogeneous coordinates of p, 2, 3, 1. And now we take a hypersurface in this. So we take one polynomial that cuts out a 1 complex dimensional space, a torus. So the hypersurface now is a constraint p equal to 0. This is a constraint, a polynomial in x, y, and z, and it must be homogeneous. And we take the degree to be 6, namely, and then the most general form is y squared minus x cubed minus f times xz to the 4 minus g times z to the 6. So this is a polynomial in x, y, z. It's homogeneous, so it's consistent with p231, and it has degree 6 under the scaling. So this is a degree 6 hypersurface, hence the name.
You can get rid of things like yz cubed by some order.
Yes, this is and this I think is the most general. Where every such polynomial one can bring into this form. So every degree 6 can be brought into this form by coordinate redefinition. In many papers you won't find actually the z anymore because the z can be set to 1 by a scaling. So one can scale locally z equal to 1 in a certain patch and then simply ignore it. This is just because oftentimes we won't really find it. And so why is this a torus? There are very intuitive ways to think why this is a torus. I'm not going to present any of these or discuss any of these. So for me it's enough to say that it's would be a one-dimensional Calabi-Yau. Namely, we have that the sum of the weights equals the degree of the hypersurface. So it's a 1 complex dimensional Calabi-Yau. So sum of the weights. So this 2 plus 3 plus 1. This equals the degree 6. So we have a Calabi-Yau 1, which is a torus, so to speak. But there are better ways to really make this more intuitive. But I don't want to discuss them now here. And finally, just for reference, this is one way to think about it. This is what leads to the Weierstrass model, or the so-called E8 fibrations. There are also other ways to represent a torus as a weighted projective space. For example, you can also take 1, 1, 2, 4, leading to a so-called E7 fibration, or 1, 1, 1, 3, leading to a E6 fibration, and then as hypersurfaces, so 2 polynomials in a higher dimensional space, etc. But this is the one that is most commonly used, and probably it is also the most general one, even though this is under investigation. So this just for references. So now we need, this is a way how mathematicians tell us to think about or to describe quantitatively the torus. Now we need to know when the torus degenerates. So we had trouble doing this pictorially, so let's try to do it algebraically. So when does the torus become singular? And now a mathematical theorem is that a T2 or any hypersurface becomes singular when at the same time p equals 0 and the gradient dp equals 0. And so in this case, say the tangent space to the curve or to the manifold cannot really be well defined. We're having situations like this where we have singularities. So let's go through. Let's evaluate this. What comes out if we want to see what has to happen. So first of all, dp has to be 0. So dyp has to be 0. So this means that y has to be 0. First of all. Second, if y is 0 and p is 0, then so has to be the x-dependent part. And I'm now scaling out z already. So this must be 0. But this is a cubic polynomial in x, so we can factorize it with a1, a2, a3 in c. These are the roots. So this must be 0. So x must be a1 or a2 or a3. But in order for also the derivative with respect to x to be 0, we have to be x minus a1, x minus a2, plus all the corresponding other terms have to vanish as well. So in other words, x has to be a1 and at the same time a2 or a3. So 2 or more of these roots have to coincide. So 2 or more roots ai must be equal. This is something that depends on the values of f and g, which we plugged in at the time. Here it's just a complex number. Oops. But now as a general fact, the roots of a polynomial coincide if the discriminant of the polynomial vanishes. So as a matter of fact, this happens if the discriminant of the polynomial p, the discriminant delta of the polynomial vanishes. And in fact, it turns out that in this case, the discriminant delta is given in terms of f and g as 22g squared plus 4f cubed. And this must be 0. So this is something, of course, that depends, as we see, on the complex structure, or on the complex, on the complex structure of our torus. F and G give the complex structure. So this is how one can now, algorithmically, so to speak, once we have such a torus, see whether or not it degenerates. And for later reference, another fact, and I'm also not going to discuss this much further now, is that the complex structure tau, in the way we defined it previously in this lattice, can be computed from f and g in the following manner, namely tau itself is not a good coordinate because it's not SL to Z invariant, but one can define a SL to Z invariant function, the Jacobi function J of tau. This is a horrible object. The Jacobi function, it's SL to Z invariant, and it contains an awful lot amount of theta functions. And from algebraic geometry, it is known, or theorem, that the Jacobi function of tau is given as 4 times 24 f cubed over delta. So this just for later reference. If we ever care what the exodilaton is in a complex structure, we need to evaluate this. And then invert this function, but this is a bijection, so mathematicians know how to deal with it. What's important for us is that asymptotically,
So it the bijection if this tau has no invariant meaning. I mean, so you get something definite now for the right hand side?
I mean, from R to, it's a bijection from C to C. Yes, I think one can.
Tau has no invariant meaning. Ask a very stupid question.
It's a single
Good point.
fundamental domain, so you can always
Okay.
put tau.
Yes, right, right. It's a bijection from C to the fundamental domain. Yes, very good. Thank you. So this J of tau has an expansion. It has an expansion in terms of tau as minus 2 pi I tau plus now higher orders, some constant, some number plus higher stuff. So in particular, we see that if delta takes a single 0, because then we expect that the torus degenerates in the way we wanted it to degenerate. So if delta is some number times, say, z, or z minus z0. Okay, now this is okay. Let me postpone this in a second because I haven't, in order not to confuse you and myself. Let us postpone this in a second because we're not.
I'm just confused. This is an expansion in large magnitude now, or?
Yeah, yeah. So it's a power series in each of the 2 pi I tau, I think. So there's this number, and then the first term then comes with e to the 2 pi I tau, and then higher orders. So near the singularity, we can invert this and then to recover the logarithm. But at this stage, since we are not elliptically fibered, there's probably no point in doing this.
So Timo, how much would you like to tell us today?
What time is it now?
12.
Wow.
I think we don't need to cover everything what you have.
Yeah, so indeed. But if we do 5 more minutes, is that fine? But anyone can leave even before, of course.
Explain it more detail than just to hurry.
Yeah. Okay, give me 5 more minutes and then we'll just kill off this elliptic vibration part. And okay. So actually there's not much more new to say now, and we're just repeating on the same thing. So this was now the torus. Given such a torus, we can see whether or not the complex structure is singular by checking for this criterion. So if we now want a fibration, we need to make F and G vary over the base. So if we do the second step, not just the torus, but the elliptic vibration, then we need to vary the complex structure. So in particular, we need to vary F and G. So suppose, for example, that we have some, say, 6 complex dimensional space, B6. And suppose it is covered by, in terms of some coordinates ui, say. Then this means we promote F to F of ui, G to ui. And the result is then the Weierstrass model y squared equals x cubed plus f of ui x z to the 4. I'm now putting the z in again. G u to the I z to the 6. So in fact, the Calabi-Yau property restricts f and g to scale appropriately, in some sense, as polynomials on the base. We won't discuss this now, but we cannot just take any polynomial. This is just to know now, all we need to know now. So what is now the position of our 7-brane? The position of the 7-brane is given by the equation delta of ui equal to 0 on B6. Because this now becomes a function of ui, because f and g are functions of ui. So this is a one complex dimensional subspace of B6. So this is a holomorphic 4 cycle. So this is a holomorphic 4 cycle. Exactly what we need. And the type of the singularity can now explicitly be computed. So suppose we have we have an explicit polynomial for our Calabi-Yau fourfold with f and g as varying polynomials, then we can explicitly compute delta and therefore explicitly see where the 7 branes live. So, for example, if we have okay, so in particular, suppose, okay, so if delta has a simple 0, say at ui minus omega 0, by this I mean where the at a position where the polynomials are fixed to something, then by inverting this from j of tau equals minus 2 pi I tau, we can indeed see that tau goes like, by inverting this, 1 over 2 pi I times the ln, now ui minus omega 0, basically, plus higher terms. So a single zero of delta means a single 7 brane. Because this was the behavior for one single 7 brane. We encircle ones and we just pick up a monodromy of ones. If on the other hand now we have higher singularities to the n, then we get a factor of n, of course, times the ln. So we have multiple branes. This is a situation which we didn't discuss so far. And the pointers also result from mathematics. Along such a single zero, the Calabi-Yau fourfold remains smooth. It's just the fiber that degenerates. But since we have more dimensions, so to speak, to go around, we don't really meet a physical singularity. In this case, the Calabi-Yau fourfold is smooth. So only the vibration is singular. And in this case, it turns out that actually the full Calabi-Yau fourfold is singular. And this is, of course, the situation which one wants. One wants to put on several branes on top of each other, because this will give rise to non-abelian gate groups. And in fact, so in fact there exists an algorithm, Kodaira's algorithm or the Tate algorithm, that allows us to detect the type of singularities, the specific type of singularities from the form of these polynomials, and thereby to read off the particular gauge group on the 7 branes. And this and some other aspects then I think we should reserve for tomorrow.
Think about questions you can also ask tomorrow. That was one.
Yeah, or whenever we meet. Yeah.
Sorry, this was just a really question. So if I have another degree fighting method that does not have a Weierstrass distribution, do the same claims about the smoothness of the fourfold? Is this just a codimensional argument, or is there anything special about it?
I think it is a speciality of the Weierstrass model, I would say. This is not the most general. I mean, it has a section. It has one section. If you have, I don't know what happens if you have several sections, say, but yeah, maybe you should. We should look that up.
Can I use? Is there a formula which gives me the pi1 of the manifold of the torus using the Weierstrass formula?
The pi1 of the torus.
The torus typically has a pi1 which is a coset. And can I use the Weierstrass formula to show that if two of these roots collapse on each other, that becomes zero?
You want to see directly. You don't, because you don't believe the.
I mean, yeah.
The answer is yes.
The answer is yes?
The answer is yes. There's a differential one form that is homomorphic, which is dx over y. So if you do the integral of dx over y over the various cycles of this branch cover, you find numbers and you can recover the information of tau that way, which is what that version is. You can see that when it degenerates, that it is decoming.
That has no pi 1.
There's also geometric ways so that the branch cuts on the plane. You can actually identify the cycles of the torus.
And you can show that the cycles go to zero when you have when the torus degenerates.
Yeah, because roots collide and then, yeah. Actually, it's nicely drawn in Clifford Johnson's book. It's in there.
It's the Seiberg-Witten story, right? Yeah, it's the Seiberg-Witten story.
Well, he does it.
Yeah.
Yeah.
Yeah, I didn't discuss that.